Welcome back. Today we're diving into Chapter 4, which is all about the properties of water. Now, you might think, it's just water. I drink it every day. What's to know? But in the world of hydronic heating, water is basically a superhero. It's the essential material that makes these systems efficient and comfortable. Let's start with two types of heat, sensible and latent. Sensible heat is the kind you can feel, literally. When a material absorbs heat and the temperature goes up, that's sensible heat. But there's another kind called latent heat. This happens when a material changes phase, like ice turning to water.
This is the cool part. When water changes phase, it absorbs heat, but the temperature doesn't actually change. Converting water to vapor takes a massive amount of energy, about 970 BTUs per pound. That's why sweating cools you down so well. Evaporation is an energy hog.
Now, let's talk specific heat. This is just a fancy way of asking, how much energy does it take to heat this stuff up? For water, the magic number is 1. It takes 1 BTU to raise 1 pound of water by 1 degree Fahrenheit. Keep that number in mind. We use it constantly.
Here is why we love water for heating. Look at this comparison. Water has an incredibly high heat capacity compared to air. In fact, a specific volume of water can hold almost 3,500 times as much heat as the same volume of air. That is wild. Because water is so thermally concentrated, we can use tiny pipes to move massive amounts of energy. A little 3/4-inch pipe carrying water can move the same amount of heat as a giant 14 by 8-inch air duct. That saves a ton of space in a building. Next up is density. We usually say water weighs about 62.4 pounds per cubic foot. But here's the catch. Water expands when it gets hot. As the temperature goes up, the density goes down because the molecules are pushing apart. We have to account for this expansion, or pipes could literally burst.
Okay, a little math, but don't panic. If you want to know how much heat is stored in a tank of water, you use this formula. You take the gallons, multiply by the temperature change, and multiply by 8.33, which is just how much a gallon of water weighs. Boom, you've got your BTUs.
But usually we are moving water, not storing it. So we need a rate. This is probably the most famous formula in hydronics. Q equals 500 times flow rate times temperature difference. That 500 is just a shortcut number derived from the weight of water and time conversions.
So if you know you need to deliver 50,000 BTUs per hour and you're pumping 2 gallons per minute, you can just rearrange that formula to figure out exactly how much temperature drop to see. It's super useful for checking if a design is actually feasible. Let's switch gears to pressure. You know water boils at 212 degrees, right? Well, only at sea level. Boiling happens when vapor pressure equals atmospheric pressure. If you go up a mountain where air pressure is lower, water boils at a lower temperature. In a closed heating system, we have to keep pressure high enough to stop the water from flashing into steam. Then there is viscosity. Think of this as resistance to flow. Honey has high viscosity, water has low. Interestingly, hot water flows easier than cold water because its viscosity drops as it heats up. But be careful, if you add antifreeze, viscosity goes way up, and your pumps have to work harder. Here is a headache for every contractor: air. Water holds dissolved air like a sponge holds liquid, but hot water can't hold as much air as cold water. That's why you see bubbles form in a pot before it boils. The air is being cooked out. We use this principle to scrub air out of heating systems. Finally, we have to remember that water is effectively incompressible. You can't squeeze it into a smaller space. This means if you push water into a full pipe at one end, water has to move at the other end instantly. It also means if water expands with nowhere to go, the pressure spikes immediately. So, to recap, water is thermally concentrated, it expands when heated, we calculate heat transfer using the 500 formula, and we have to manage air and pressure carefully. Master these properties and you're well on your way to understanding hydronic design.